Let's start with statistical methods. So first, is there something from last week that you are confused about and feel you have to clarify before we can get started today? No, you don't feel like that. Good. So then the aim for today is to continue our formulation of the general linear model. So we still talk about understanding this equation, and we made some progress last week in the sense that you are now familiar with this notation. So you know when you see that, what does that actually mean? Maybe I can ask you. So what does this thing that I just wrote, what does that mean?
It's a matrix.
It's a matrix, and what can you say about this matrix?
The dimensions U and P.
That's actually my N, but looks like a U, so you're right. And sorry, and what else can you say about it?
The real numbers.
The real numbers, exactly, yeah. And if you see that, or if you see actually that X is an N by P matrix, and you see this matrix product here, what else can you say in terms of what can you say about beta? If this matrix product is a sensible matrix product?
Beta has N dimensions.
N? What?
N by something else.
No, it has P rows, yeah. Because you can only multiply something. You can only multiply two matrices if the inner dimensions agree. So that was this little formula. For example, if you have n times m, then a matrix product only works if the next one is m times something else, for example, p. And yeah, and actually you cannot say much more in this case. What is the case is that actually beta is a p-dimensional vector, so it's a p times one-dimensional matrix. We will see that again. But yeah, this is basically where we left off last week. So the aim for today then is to first give you a working example for this x beta expression. And that's what we can call, maybe let's call it the simple linear regression matrix. So that's an example for the GLM, and as I told you in the first lecture or first lesson, that the GLM is a unifying perspective on many statistical techniques, for example, ANOVA, t-tests, f-tests, and whatnot. And we will talk about the GLM in fairly abstract terms for most of the term, until in the end we fill in these specific statistical techniques. But to give you one statistical technique that can always be helpful as an example, we will formulate this simple linear regression matrix example of the GLM, where it's then very concrete what the x and beta is and what also the y is. And once we talked about it, also the epsilon, and there's also a graph and so on. So you can really associate a concrete instance of the GLM with this general equation. So that's the aim, the first aim. And then the second aim is that we have to start talking about probability and probability theory, maybe, if you want, because we have to get started on this epsilon. So the epsilon is a random component or stochastic component of the GLM, and we have to get into that. So that's the outline for today, and let's see how far we get. We will then, once we made the detour through probability theory, including actually Gaussian distributions. We also have to talk about multivariate Gaussian distributions. Once we finish this detour, we will come back to the formulation of the GLM. Yeah? But first, a concrete example, namely simple linear regression matrix. So that's now simple linear regression. So you all had statistics undergraduate courses. What do you remember about simple linear regression? Who would like to share their knowledge about simple linear regression? Why don't you share your knowledge about simple linear regression?
It's gonna be embarrassing because it's been a while since I've done it. And
Yep.
I remember that there's correlations and regression, and correlation is looking for a point that two graphs have in common. And regression is reducing data by a point.
Okay, so that's kind of how would we call that, high level knowledge, and I assume you were tested whether there's a difference between regression or correlation, or why do you remember them together? It's not really clear. Okay, so we talk about regression. Anyone else want to share their knowledge on simple linear regression?
Maybe like an association where we can find an equation that relates x to y,
And how?
y is independent and x is dependent.
And how does this equation look?
Y equals m, x equals b.
Yeah. So you said m. Maybe I just take another letter. So I take ax plus b. And do you have a picture in your head also when you a line? Yeah. So something like this maybe. And then you already said there's something called x, and you related that to the independent the independent variable in the talk of psychology statistics. So that's the IV. And then there's something called y, and that's the dependent variable. And it's about, kind of this relation. And what is a little bit missing here are some data points. And I guess you also somehow learned that you want to find this line that goes through these data points or something, I assume. So this is, I think, where I'm starting. So basically, this is what I think that you have seen before. And now I'm trying to make this a little bit more precise and relate it to the notion of matrix multiplication as we introduced that last week. Yeah, and also then show you how this is a special case of the GLM. Good. So I think I just do it. So the first thing about simple linear regression is that it's actually a statement about the values that a dependent variable takes on for given independent variable values. So what is a little bit confusing about this equation is that it is not really focused on individual data points, but it says something like y, a, x, and b, and it's not really defined. So the first thing that I will now do is to write this a little bit more careful, in the sense that we consider the case that we actually have n data points. So we have an index I going 1, 2 to n. So for example, n being 5 or 10 or 100, depending on the size of your data set. And for each of these index values, I'm telling you now that a simple linear regression actually corresponds to this model, where all of the things that you see there are real numbers. So yi, a, xi, b, and also epsilon i, they are all scalars. So they are just numbers. For example, 1.2 minus 0.5 pi, whatever. And what we are going to focus on, because this is of course related to the GLM, and we haven't talked about probabilistic aspects yet, what we are going to focus on is this part here, without the epsilon I. So to write a simple linear regression in matrix notation, we will actually focus on the on the deterministic aspects, and leave this epsilon I for a little bit later. So I will use that then as a bridge to introducing probability. But for the moment, we focus on this yi equals axi plus b. So more concretely, if we now say I goes 1, 2 to 5, what we have is the following set of equation. I just write up, where I ignore the epsilon I for the moment. So we now have here 5 equations, and what this is related to in terms of, if you think about you acquired data, then you can, for example, think of the following. Examples never really make sense, but let's say that yi is the shoe size of someone, and xi is the height of someone. Yeah? And both, for example, measured in centimeters or whatever. So I'm always a little bit reluctant with examples because I'm trying to establish abstract concepts, but I know that it helps to also have maybe a little bit concrete example. So what these equations now want to say is that you have 5 values of heights. Yeah. So for example, let's come up with 5 values for heights here. For example, 1.5, 1.6, 1.7, let's do it like this, 1.8, 1.9. Yeah, so these are 5 values for height now. And these equations here on the left, they say that the shoe size is given as the product of each of these height values with a value a, and plus another value b. Yeah. So then let's call this here our xi again. So then let's come up with a number a. So let's say a we define as 0.1, so 1 over 10, so that it's relatively simple if we now want to evaluate y1. So what do we get for y1? If so I haven't told you what b is. Let's say b is 0.02. Now we want to calculate y1 given x1, so 1.5, and based on these constants. So what's y1? 0.17, yeah. So we do 0.1 times 1.5, that's 0.15 or 0.15, and we add 0.02, so we get 0.17. Yeah. Now, what do we get for y2? Please say it, otherwise I will not go on. 0.18. Yeah. Good. So I assume you got the idea, so I will not ask you for the remaining and just write them down. If I'm writing something wrong, let me know. So, good. Now what I actually showed you, so let's go back. So I said this is the general equation for n data points, and now I've shown you that if we have 5 data points, this means that we have 5 of these equations, and then we actually did a numerical example here where we actually put in numbers. Now I want to plot these numbers. So I want to make a plot out of this. Wonder whether I have some lines, but I don't think so. Go away. No, go away. So I have to do it by hand. So now we want to plot these numbers, or I want to plot them. So it kind of makes sense to have 1.5 here, 1.6 here, 1.7 here, 0.8, 1.9. Yeah, that's enough. And on the y-axis, it makes sense to have start from 0.17, 0.18, 0.19, 0.20, and 0.21. And now these are our xi values. And these are our yi values. So that's our independent variable. That's our dependent variable. And now we can basically put in what we've just computed. So 1.5 yields 0.17, and same way for the remaining ones. So that we get these points, and of course they are all on a line. So they are on a line. If I could easily put a line through them, yeah. So that's essentially what this aspect of the simple linear regression equation wants to tell you. If you have values for xi, and for a and b, then you can compute values for yi, ignoring epsilon I, or saying that epsilon I is 0 all the time. Yeah. Now, what does this have to do with matrix multiplication? Well, if you look at this here, so if you look at our equations that we wrote, what we actually can also view this as, at least here on the left side, we can view this as a vector. Yeah, so we can view our y1, 2, y3, y4, and y5 as a vector. So we can basically write this in vector notation as y1, y2, y3, y4, y5. And as I told you last week, vectors are just lists of numbers. So now I wrote a list of number here, and it's has 5 entries. Another thing that we have seen is that we have also a list of x values going also from 1 to 5. So we can basically also write those as a vector. Let's get rid of this here and focus on here. So we have our x1, x2, x3, x4, and x5. Maybe let's leave that bracket for now. And then you see that we multiply all of these x values with a constant a, right? So if there would only be these x 1, 2, 3, 4, 5 values, we could now basically write a matrix product where we put in a here, yeah, and then if this is a vector now, the x1 to x5, you know how to do the matrix multiplication because you all trained yourself to do that. So you have x1 times a, x2 times a, x3 times a, x4 times a, x5 times a, and these are exactly these values, only that they are in reverse order. So a times x1 is the same as x1 times a. Now it's not quite complete because we also have to add this value b there. And now the magic happens, and it's happening exactly in this second now, because if you put a b here and a 1 here, and then you consider this, consider this a matrix. How do I do that? Like this. And I just put the BA a little bit to the left. BA. If you now compute the matrix product, you get exactly the equations above. Because if you compute the matrix product, you need to take the row and multiply it with the column. So you have 1 times b, that's b, and you have to add to it x1 times a, that's a times x1. So you actually reproduce this equation by doing the matrix product of this with this. Yeah, and this, as you can easily convince yourself, holds for all the rows. So let's look at the 4th row. So if we want to compute x4, we have to compute 1 times b plus x4 times a, which is just this thing. Yeah. So now what we have done is that we have fairly concisely expressed our set of equations here, our for 5 data points, with a matrix that has 5 rows and 2 columns, and with another vector that has just 2 rows. Yeah. So we have, now I'm expressing that a little bit more concisely. So I'm calling this y1, y2, y5 vector, I call that y, and I call this matrix with the column of ones and the column of the values of the independent variable, I call that x. And I call this vector with the b and the a in it, I call that beta. Yeah. So this is now x, and this is now beta. So the other way around, if so we can also start, okay, y is a 5-dimensional vector, so you should think of something like this. X, I'm telling you now, if it takes this form, is called the simple linear regression matrix. And beta, which, if this is a simple linear regression matrix, it has to have 2 rows, otherwise the matrix product is not possible. That's the parameter vector. Yeah. So we have now basically re-expressed this thing that you were familiar with in matrix form, but for a special kind of matrix X and for a special kind of a parameter vector beta. Special in the sense that if it's a simple linear regression model, there needs to be a column of ones, and there needs to be the values of the independent random variable. Now one can ask what the meaning of this beta and of these b and these r parameters are, and that's can be explained fairly quickly. So assume, maybe we do that visually. Assume you have values for the xi going from 1, 2, 3, 4, 5 and starting at 0. So x1 is now 0, and you have any value for a. So if you, for example, a equals 10 or a equals -2 or whatever, if you multiply 0 with this value a, you always get 0. So your the line that you would come up with always starts at 0. However, the simple linear regression equation says there is this plus b. Now, if this plus b or this b better, if the b is not 0, so for example b equals 2, then for this point where you do a times x1 and x1 is 0, then you already are at 2. Yeah, so this is not where you are. Oops, there goes my whole axis. So you end up here already. Yeah, so that's your a times x1 plus b, because b is now 2. 1, 2, 3, 4, 5. X1 is 0, so you end up here. And then you've seen already what the a does. So it essentially scales the values of the independent random variable, independent variable. I always want to say random variable, but it's an independent variable because it's a fuzzy psychological concept. And you've seen here what it does. So it scales the 0.1. It scales the 1.5 by 0.1, and then it translates directly into the slope. So you see that here the difference is 0.1. Okay, that was not the nicest explanation, but we will come back to the notion of a slope when we do the calculus bit. Yeah, so for now, and also to memorize things about this before you completely understand them, which sometimes helps, is to memorize that A, in our case, is something like a slope, and B is something like an offset. And then you can always ask yourself again, why is it called offset and why is it called slope? And then you can clarify that in your head if you think more about what's actually happening in this equation. Okay, so that's now the more important thing is actually this matrix formulation of the whole thing. So that's really important, rather than maybe the interpretation of the parameters, although there's always an interpretation to the parameters in any kind of GLM, and one has to think about it, so it doesn't hurt. But I think for now, if you get used to writing simple linear regression in terms of matrix formulation, that's already something, and then you can start thinking about why it's called slope and offset. One thing I want to add before we go on, and actually also to motivate to go on, is that of course the situation here looks quite different from what you have seen when you saw simple linear regression in undergrad statistics, in the following sense, namely that what I've shown you now with this matrix formulation of the simple linear regression, the only thing that can always happen is that you get straight lines. Yeah, so you get things that are on a straight line. Yeah, and you all know and have seen pictures like that, real data somehow is never really on such a straight line. But you see, but there's some deviation. Yeah. So the data points, which I'm now putting up in blue here, they might not actually be on the straight line. And then you might have heard that you use ordinary least squares to find the straight line. But what is more important right now is that there is this deviation between what the matrix equation for simple linear regression says and the real data point. Yeah? So you see there's this deviation in the y direction. And this deviation in the y direction, that is this epsilon. Yeah? So here we have again 1, 2, 3, 4, 5 data points. So that would be our epsilon 5. That's epsilon 4. Actually, this deviation here. This would be epsilon 3. Oops, now I miscounted. 5, 4, 3, 2, 1. Well, we have, no, it's fine, sorry. That's epsilon 2, that's epsilon 1. And as you can see, epsilon, or maybe let's stay in blue, epsilon 5 is something negative, so it's minus 0.01, for example, if we are for our x5, we are at, for example, let's say 4, let's say this is 4, and our a is 2, so we have so a equals 2, and our b, let's say, equals 0. So then x5, 4 times a equals 2 is 8, so we are at 8. That's the prediction of our simple linear regression matrix and the parameters. But then there's something in addition. There is this epsilon 5, which is in this case minus 0. It's a little bit larger. It's more like minus 1. Say, call it minus 1, minus 1.1. So there is this additional thing which makes the simple linear regression more like the simple linear regression pictures that you have in your head. Yeah. So to make this more precise, so I'm trying to express things somewhat informally so that it kind of rings a bell. What we have looked at is actually the expectation of the simple linear regression models. So we have looked at, with the matrix part, we have looked at this bit, which is the deterministic aspect of the GLM, and it makes a precise, non-random prediction, which is also, as we will see later, the expectation. But for that, we really have to go into probability theory. And there is something in addition in the model, as you have seen it previously, namely for each of the data points, the model doesn't just say, okay, it's all these, my predictions are all on this line, but there is also a prediction of some random aspect. And the whole point talking about this epsilon in the last couple of minutes was to say we have to talk about probability theory. Otherwise, we cannot make progress. Otherwise, we can only predict straight lines. And we all know that data hardly ever lie on straight lines. Yeah. Good. So I think I stop here and ask for questions. So who is confused about what I've just shown you? And if you don't, so who is not confused at all about anything? Please raise your hand. Not confused about it at all. So the rest seems to be slightly confused. So then try to figure out what confused you and ask as a question what confused you.
Yeah, so the way I learned it in my undergraduate was that the epsilon is the error term that you do not model. It's just like the description of the reality, and then you always have the y with the hat, which is the model. Mm-hmm. But as I understand it, you're telling us now that we do model the error term.
Yeah, that's a good point. So it's a question. Yeah, so it's more like a philosophical question. So yes, I would say, of course, you model the error term because at least in the parametric statistical viewpoint of the GLM that we are going to continue on, because we want to compute t and p values, you need to make some parametric assumptions about the error term. And we will make the assumptions that these error terms are Gaussian distributed, and what that means we go on about. And this also then relates to the question modeling or estimating parameters in a maximum likelihood sense rather than ordinary least squares sense, but we will also come back to that. But yes, so we will model the error terms in the sense that we specify a parametric distribution for the error terms. You can also not do that and then do ordinary least squares estimation, but then you cannot do parametric inferences like computing t or p values. But this will only get clearer later, so I don't want to expand on that. But it's a good question. So from my perspective and the general probabilistic modeling perspective, the entire model is this thing, or in matrix form y equals x beta plus epsilon. And we will go on about that. But you have something else on your mind?
I was just wondering that you do not attempt to explain 100% of the data, right? There still remains.
Yeah. So this is so the prediction of the model will deviate. So the prediction of the model, that's the line. So that will deviate from the actually observed data, but to make the inference aspects, so to basically allow for t and p values or Bayesian and posterior probabilities, you need to still make a commitment about these remaining deviations and make the statement that you assume they are normally distributed. What that means, we will come to. A very good question, yeah. Other questions? So there were not everyone was not confused. So those people who were also confused, what was confusing?
Why we put 1 in front of the x's? I mean, not here. What? Yeah, here.
This one?
Yeah.
This one here?
Yeah.
Yeah, this is actually crucial. So make sure that you understand exactly this. I'll tell you in a second. But this is crucial that you understand why there needs to be this column of ones in this matrix. And this you can only understand this if you really learn to do matrix products by hand. So if you did not follow my advice to train yourself in matrix multiplication, this might be opaque. I'm telling you again, but I also know that you can only really appreciate this column of ones if you trained yourself. So the reason is that if you multiply this matrix here, so this matrix with the ones and the x's, with this vector here, with the b and the a, then you always multiply 1 times b. In each row, you multiply 1 times b, and you have to add to it a times x1. So only by introducing this column of ones can you actually reproduce these equations if b is not 0. If b is 0, then you can reproduce them also just by having a vector of the x5 and multiplying by a. But if b is not 0, you need this 1, which is also called a dummy variable, to add this offset of b to each of these products of the a and the x. But yeah, so the important thing here really is matrix multiplication. So we talked about matrix multiplication last time because it goes into every single prediction of the GLM. Also, if we later formulate 2 sample t-test in terms of the GLM, you need matrix multiples, and we just need them. So make sure, so really a good homework, so now the B is blue, a homework is to write down a matrix with values. So write down a matrix like this. Maybe like this, and a vector like this. And compute the matrix product. Yeah. This is really something you have to do. If you don't do that, things will be confusing. Please do that. Yeah? Other questions right now? No. Good. So, yeah.
I have a question.
Yeah.
Because I understand you have to put the 1 there. Can you just do it? I'm just changing. You can just add ones into a matrix and change the matrix. And...
Well, so the way this works is that how can I explain that? So this is you can define matrices however you like. Yeah. So you can say, okay, I want a matrix, so let's define a matrix, and then you have a matrix. The thing, what I'm just showing you is a special case of this equation where I say, okay, we can have a special case of x which consists of a column of ones. So a column of ones and a column of values of an independent variable. And now I've just made a very abstract thing, namely an x, a little less abstract by saying it's a matrix with a column of ones and a column of values x1 to xn. And in this sense, I can do that. Yeah.
And it has to be a 1 because if you multiply it, it's the same.
It has to be a 1. Yeah, so it has to be a 1 so that.
Pick a 2 or something because it will change.
Yeah, that's a fair point. So it could also be a 2. What then changes is the interpretation of the B. Yeah. So here I try to explain the interpretation that B is the offset. So B is what you have to add to your line. For example, if you are at 0, then you don't make the prediction 0, but you make the prediction 2. And this holds if B equals 2 and in the matrix you have a 1. Yeah. Now, if you in the matrix, for example, have a 3, then you have 3 times 6. And then you have here, then you end up here at 6. But the, where was I? B is now, so in the matrix you have a 3. You ask questions. You have in a matrix you have a 3, and then if B is 2, you still have 6, but let's make that different. Yes, mean question. So in this case you would have 6, and then this 2 here is not the offset, but because the offset is 6. So you can use other dummy variables, but then the interpretation of the parameter changes. So if you want to stick with the interpretation that the parameter that models the offset in the sense that if you're at 0, you have to go 2 or B up, then it makes a lot of sense to have a 1 in there. And the convention is to have a 1 in there. Also, when we later talk about ANOVA, it's always based on 1s, dummy variables. Based on the numbers, these numbers just a 1, like a 2 is a number, so you could do it differently, but then the parameter interpretation changes. Yeah? Okay, so then let's stop here before I get another dangerous question where I then invalidate everything I said before, but I didn't. I got the curve, as you say in German. Ich habe die Kurve gekriegt. So let's stop here and then now talk about in the next sessions about the thing that we need somehow an idea about these epsilons. Okay, let's have a break.